Hello, this is the lecture on homogeneous systems of equations. Systems of equations that have zero vector and the right side as the vector of constants. Whenever this b is exactly equal to the zero vector, that would be the case in which we have one equation that equals 0, another equation that is equal to 0, another equation that is equal to 0, and then we have a total of m equations, and this is also equal to 0. So all the right sides of these equations in the linear system are equating to 0. And that is the case in which we call the system homogeneous, a homogeneous system of linear equations. Here is an example in which we have that scenario. In this example, we have 4 variables. So we have 3 equations, and you can see we have here n equals 4, where n denotes the number of variables. Okay, so we have m equals 3 equations and n equals 4. And so again, what we would like to do is to compute the solution set for this system. And but before we do that, before we get involved in computations of reduced rotational forms and stuff, look at this question. Can you quickly find a solution? Oh, quickly. Well, what does that mean? Okay, so by inspection, is it possible to come up with a solution for this system? And the answer is, well, maybe I shouldn't spoil it, but look at the first equation. What happens if x1 were evaluated at 0, and x2 evaluated at 0, and x3 evaluated at 0, and x4 evaluated at 0? If that were the case, if all the values, if x1, x2, x3, x4, if all these values of the variables, okay, are evaluated at 0, then the equations are always satisfied. And that's a nice property of these systems, the homogeneous systems of equations, because they are always consistent. There is at least one solution for these systems, and that solution is the solution of the vector of zeros. And because when you evaluate 0, you obtain 0, then that solution of the system is called the trivial solution. Some people would say, oh, that's trivial, meaning that that is obvious. Okay, so here in mathematics, sometimes we prefer to use the word trivial for solutions that are quite straightforward to find or to calculate. And some mathematicians also like the use of the word obvious. So we have a theorem that says basically what you just point out. Suppose that a system of linear equations is homogeneous, then the system is consistent, precisely because the trivial solution is always a solution of a homogeneous system, which is what we have stated in this definition. So homogeneous system of equations with n variables, then the solution in which all the variables equal 0 is a 0 vector and is called the trivial solution. Here comes an example. In this example, we have 3 equations, 3 variables. So here we're going to say that m equals 3, and n, the number of variables, is also 3. When we collect the coefficient matrix and augment that with a column of zeros, then we would get a matrix that has 3 rows and 4 equations. Okay, so the augmented matrix would have 3 rows, 4 columns. Excuse me, 3 rows, 4 columns, and then when we row reduce, okay, so A being the augmented matrix, for example, we say that A row reduces to this matrix that we have here. So in this case, we have that the number of non-zero rows, little r, equals 3. Okay, and here set D, collecting indices of pivot columns. That set has 1, 2, and 3, and set F contains 4 only. Okay, so this tells us that this is a scenario in which the system is consistent, and because R equals the number of columns, then there's no free variables. Um, remember that this is the RREF of the augmented matrix, so always the last index is neglected. There is only variables x1, x2, and x3, and what we can read from each of these equations is, if you look at equation number 1, this is telling us that 1 x1 plus 0 x2 plus 0 x3 equals 0, right? So this is telling us that x1 equals 0. And the second equation says a similar story, 0x1 plus 1x2 plus 0x3, this equals 0, and this implies that x2 equals 0, and similarly we would 0x1 plus 0x2 plus 1x3 equals 0, this implies that x3 equals 0. So the only solution for this system based on the RREF calculation is the trivial solution. And precisely that is confirmed by a theorem that we had previously mentioned, and that tells us that when the number of columns matches the number of non-zero rows of the RREF, then the solution set contains only a single solution, and in the case of a homogeneous system of equations, that solution would be the trivial one. So in this example, we have, again, here we have 3 equations, and the number of variables is also 3. When we row reduce the augmented matrix, which is 3 by 4, we find that R, number of non-zero rows, is 2. So unlike in the previous example, n, this number is smaller than the number of variables. Okay, and so this tells us, the REF is telling us that there is at least one row of zeros. Okay, that's another way of thinking of this. When there is at least one row of zeros, there is no leading one on the last column. The system is consistent, and this is indicating that indeed this will be one of those scenarios with dependent variables and free variables. Therefore, the system will have infinitely many solutions. Okay, so here D will be the set of indices with indices 1 and 2, and F would contain indices 3 and 4. So right away we are concluding that the variables x1, variable x1 and variable x2, these variables are going to be considered dependent variables, and in this case the variable x3 is going to be considered a free variable. Okay, so let's write the solution vector, which has entries x1, x2, and x3 in terms of what we see from the RREF, right? So the first equation is telling us 1 x1 plus 0 x2 plus 1 x3 equals 0, and since x1 is dependent, we can write x1 equals minus x3, and from the second equation we have that 1 x2, 0 x1 plus 1 x2 minus 1 x3 equals 0, and this implies that again x2 is a dependent variable, so we can solve for x2 and write this as x2 equals x3. So the vector x1, x2, and x3 can be written in a way such that x1 and x2 are expressed in terms of the free variable. X1 is negative x3, so that's the expression we have here first, and x2 is exactly equals to x3, which is what we have second. Okay, so here the solution set is represented in terms of the free variable, which in this case is x3. So here is another example in which we have, in this case, we have 3 equations and 4 variables. So in this case, n equals 4, which means that the augmented matrix will be a matrix that has 3 rows and 5 columns, right? So you can see 2, 4, and 5. And since little r, in this case, little r equals 2, then we see right away there is a row of zeros over there. There is no 1, there's no leading 1 on the last column, so that's a good confirmation. This will be one of those cases this system is consistent and is going to have a solution set with multiple solutions. Okay, so importantly, here indices, this is one, column 2, so the set of indices, capital D, this would be containing 1, 2, and let me draw something. This is in the set F for indices, columns 3, 4, and 5. Okay, we're gonna disregard column 5, but this is telling us that x3 and x4, these two are considered the free variables. Okay, the free variables. So what we can do next is look at the first row and write, okay, 1x1 plus 0x2 plus 3x3 minus 2x4 equal 0. And since x1, so x1 and x2 are the dependent variables, x1 is a dependent variable, we can solve for x1, okay, and say, okay, this looks like minus 3x3 plus 2x4. We're solving for x1. And we can do the same from the second equation over there, 0x1, 1x2 plus 1x3 minus 3x4, that equals 0. And from here, since x2 is dependent, we can say x2 equals minus x3 plus 3x4. So we have an expression for x1, another expression for x2, and we can substitute that into the vector containing x1, x2, x3, and x4, such that, in such a manner that x3 and x4 are expressed as quantities that are on their own, they're the free variables, and then we have expressions that are substituting the first entry and the second entry of the vector. So this notation, this will be the solution set. x3 and x4 are allowed to take any possible values or the complex plane. x3 and x4 are assumed to be complex, and this denotes the solution set for this homogeneous system of equations.